Very good afternoon, everyone. After lunch, it's not the perfect time slot for a presentation, but I try to keep you awake. Yes, my project is improving the quality of bananas in the post-harvest supply chain. I'm Indika Fernando, and my supervisors are Dr. Jing Fei, Professor Roger Stanley, and Dr. Hussein Ishai. Looks do matter. The looks of fresh produce is a critical factor for consumers' purchase decision, not only in Australia, but everywhere in the world. So for bananas, there's no exception. Appearance quality has been a crucial factor for the consumer's purchase decision in Australia, as per the studies conducted in 2011. Given both these bananas are priced at the same level, a rational consumer would go for the one without bruising, one that looks good. That is why the appearance quality is so important when it comes to bananas. With that, let me give you a bit of a background to bananas. It's one of the staple fruit crops in the world, with a world production of 114 million plus tons metric tons as at 2014. And it is the largest horticultural industry in Australia, with a farm gate value of 600 million Australian dollars. It's estimated that about 5 million bananas has been eaten each day in Australia. And this problem of cosmetic imperfections cost the industry about 23 million Australian dollars per annum, according to a published study conducted in 2011. This might be much higher now. And most importantly, in this project, 95% of all this banana production is coming from the region of northern Queensland. It is this region that we're talking about. 95% of the entire production originates in this region, which results in long supply chains exposing banana fruit to prolonged vibration and also shocks in transit, which may cause cosmetic damage, cosmetic defects in this fruit. So what exactly is the problem? Green bananas, which originate in the farm, end up in two different scenarios. One without bruising, and of course one with bruising. So the problem could be explained simply in 4 W's. What, where, why, and when this problem occurs, and what can we do to minimize these cosmetic defects. So to understand the response of banana fruit to vibration, we did a simple simulation study using a home vibration simulator. So we vibrated these packaged bananas for 15 minutes at 3G peak to peak vibration at 10 Hertz, and this is how a hand of bananas were looking before that experiment. So I'll just play this video. We don't have sound, it's just vibration. So this is intense vibration. This is just a 10-second clip of that whole 15 minutes. So after that, they were looking like this. So true that it is intense vibration, but on the other hand, not so intense vibration for a longer duration would have more or less same effects on bananas. According to literature and past studies, these cosmetic defects, the problem of cosmetic defects can be viewed in different angles. One major reason would be microbial activity, which we are not looking into within this research, but mechanical damage. Mechanical damage could be influenced by atmospheric conditions and also fruit properties, such as the curvature of the fruit, firmness, rigidity, peel hardness, etc. Mechanical damage could be occurring due to 3 types of forces: compression, impact, and vibration. Now what you see here is what is being reported in the industry: several types of damages, such as bruising, neck damage, scuffing, fruit rubs, etc. We need to find out, if you have to solve this problem, we need to find out the relationship between these forces, these basic forces, and the industry reported damages. So we need to find out where exactly which node or link in the supply chain has the most susceptibility to damage. So this is a typical banana supply chain. Farm is somewhere here, and we have the pack house, and this is the handling chain and the retail lane. So to identify where damage occurs, in my research, I'll be inspecting the supply chain at 5 distinct points and quantifying the damage at these locations by ripening bananas to stage 6 so that all the latent damages would become visible once ripened. So it would be a qualitative study at these two ends, in the pack house and at the retail end, to identify the potential causes of damage, and we'll be quantifying vibrations and shocks, during handling and in transit. So this is how we are going to quantify damage. As at now, we have two alternatives. One is using image software, and the other one is using MATLAB image processing toolbox. So both uses image processing and image analysis techniques to objectively quantify damages on bananas. So how are we going to quantify the vibration and shocks that occur throughout the supply chain? Is with the use of these sensors. Now, the commercially available sensors, what you see here, is not capable of recording data from end to end, particularly in extended supply chains, which runs for 120 hours. In other words, the journey from Tully to Melbourne would take about 5 days in transit, which means about 120 hours. So in order to identify the locations of shocks and vibration, these sensors has to be sampling throughout without overriding data or without losing any data. So we had to experiment we experimented three sensors, and there were different stages. Why there had been different stages is that we improved from one stage to the other the battery consumption, the power consumption, so that we could sample for a longer period of time and also improve the memory capacity. Using this, these sensors are capable of sampling 3-axis acceleration, or in other words 3-axis vibration, timestamp, GPS coordinates, and also temperature. GPS coordinates provide a spatial quality to data to understand where exactly these shocks occur along the supply chain. Using these sensors, we were conducting a pilot study from Launceston to Brighton in Hobart. The objective of this pilot study was to understand how these sensors work and whether these sensors are producing results as comparable to what has been published already, what has been reported in past studies, and also whether we can use these sensors in real-world application to test our hypothesis. So we used two types of sensors. Two are in wireless mode, and two of the sensors were in self-logging mode. And this is what the vibration profile looked like from Launceston to Brighton in Hobart. This is the time series data. X-axis is the time, and y-axis is acceleration. I don't know whether it's clear. Acceleration in milli-Gs. So G is the notation for Earth's gravitational acceleration. So this is in milli-Gs, which means it's multiplied by 1,000. We encountered 182 shocks, more than plus or minus 2G. That means more than plus or minus twice the gravitational acceleration of Earth. There were 182 shocks as at that, and 14 shocks more than plus or minus 3G, and 3 shocks more than plus or minus 4Gs. So this can be very detrimental to these products being transported. Now, most of the time this is due to road unevenness, and also at that time there was, even now, there's road construction in between Launceston and Hobart, which results in a lot of these shocks. And this is the difference. This graph shows the difference between a transient shock and vibration. Vibration is mostly in between plus or minus 1,000, which means plus or minus 1G, and transient shocks are impulses with a pre-shock stage which exceeds this level of vibration. And we can develop these vibration profiles using those captured data to do simulation. Now, how are we going to do simulation is using vibration and shock simulators. Now, these are huge tables that vibrates that we can simulate once a profile is given. Now, when the simulation is going, we can actually recreate the conditions in transit to test different parameters. which might be useful in developing solutions. And on the other hand, we can quantify the compression force, which might be responsible for compression bruising and also neck damage in bananas. Now, ideally, this package should hold the weight of this box by 4 corners. But if the weight is concentrated here, it will bend the package like this, and it will compress the bananas underneath, which means it will result in compression bruising. And since the crowns of these bananas are partially fixed, and when individual bananas get a compression force, it can result in neck damage. With that, I'll go to contributions of this project. This will deliver recommendations to decrease mechanical damages in bananas, identify where damages occur in supply chain, determine the relationship with vibration and shock data with level of banana damage, and characterize vibration profiles in Australia as a whole. With that, I'll conclude my presentation with a huge thank to our project partners, ARC Training Center, Costas, Woolworths, thank you very much, TIA, University of Tasmania, and Tasmanian government as well. Thank you so much.
Thank you.